everyone, we're going to start with the using chemical analysis to determine the origin of wines with machine learning. My name is Abigail Mora. We have Vivian Ho and Cristobal Padilla. The goal of the project is to correctly classify the origin of the wine using a machine learning model and the chemical composition of the wine. Our dataset it's imported from UC Urban Machine Learning Repository. The dataset is slightly unbalanced, favoring wine number 2. Chemical analysis of wines grow in the same region in Italy, but derived from 3 different cultivars, which means we have 3 wines and they come from 3 different places. Our dataset is tabular and contains 178 entries, and we have 13 features found in each of the 3 types of wine. Our dataset target 3 vineyards, which is 3 classes. The attributes are alcohol, malic acid, ash, alkalinity of ash, magnesium, total phenols, flavonoids, non-flavonoid phenols, prothocyanidis, color intensity, hue, OD280, OD315 of diluted wines, and proline. And this data, in this module, we find flavonoids and proline more important, carbon relationship. And the data counts where we're able to see that wine 2 have slightly more entrants than wine 1 and wine 3, which makes the data imbalanced. And to mitigate this issue, we ensure that the dataset was shuffled enough times for the models to be fair. And for testing, we use a stratified K-fold validation. The future correlations are shown in this head map for the parameters. Flavonoids and proline have some of the biggest correlations, so they have like more relationship, as I had said before. Flavonoids are phytochemical compounds present in many plants, fruits, vegetables, and leaves, with potential applications in medical chemistry. Flavonoids can possess medical benefits, including anti-cancer, antioxidants, or anti-inflammatory components. A large percent of the total amino acid left in the wine is in the form of proline. The amount of proline in the wine can vary from 0 to 90 of the total nitrogen. Our hypothesis is that these 2 features are critical to identify the vine year, since they're like most shown and they're like related. Our model 1 is random forest, and we start with a grind search, which tested 72 models, and from those with these hyperparameters, we get the best model with the best results, which will be 100 estimators, criterion Gini, max features log 2, min sample split 4, and max zip 3. And our evaluation is shown by the confusion matrix with the accuracy of 0.98, precision of 0.98, recall of 0.98, and f score of 0.98. K-fold cross validation shown our accuracy was 0.99, precision 0.98, recall 0.98, and f score 0.98. And from the feature importance run, we saw that our random forest classifier, proline and flavonoids were the most important features, and ash and non-flavonoid phenols were the least important for this module.
For our second model, we decided to go with the gradient boosted tree. So our initial grid search, we focused on the following hyperparameters: the number of estimators, the learning rate, the subsample, and the max step. And after a couple, once as we did an exhaustive search using these hyperparameters, we came up with the following parameters that gave us the best model. Is 100 estimators, a learning rate of 0.001, sub sample of 0.8, and a max step 3. Upon initial evaluation of the model, we see that our accuracy or the accuracy of the model was around 98, precision 98.98, recall 0.98, and F1 score of 0.98, which seems to be very consistent, and it can be seen from the confusion matrix. It apparently only made one mistake. But doing the k-fold validation, we see that the accuracy went down. Accuracy went down to 0.95, precision went down to 0.95, recall went down to 0.94, and the F1 score went down to 0.94. This is to be expected given that our initial data set is unbalanced. So we believe that some of the folds gave better results. Others gave, well, we can see some worse results. The average out to about 95. So again, consistent with our observations. Feature importance of this model, it highlights the proline as a key factor, which we believe to be based on the correlation heat map. We were expecting something like this. Also, flavonoids were highlighted. So this model is consistent with our hypothesis. For our third model, we decided to use a support vector machine. Again, we deployed a grid search strategy. And for the hyperparameters, we focused on the regularization coefficient, the kernel coefficient gamma, and two kernels. And after the grid search, the best model that we found was regularization coefficient of 10, the kernel coefficient gamma of 0.01, and a linear kernel. Our initial evaluation of this model basically gave us a perfect score: accuracy of 1, precision of 1, recall of 1, and a score of 1, which is, well, very promising. After doing the k-fold validation, we see that all scores dropped. Accuracy went down to 0.97, precision went down to 0.97, recall and F1 scores also went down to 0.97, around there. And as we can see in the confusion matrix, there were a couple of errors, not too many, but there were a couple of mislabelings. Again, this is consistent with what we mentioned about the unbalanced data set. We weren't expecting to have a perfect score. Nevertheless, the support vector machine model gave excellent results. And now looking at the feature importance from this model, we see that proline, this model focused primarily on proline. That was the main indicator that it utilized. However, for some reason, flavonoids were not as important for this model. It focused on other features, which was a bit surprising. But nevertheless, at least we can see that proline only plays a major factor in wine classification.
For our last model, we did a neural network. We had 4 layers. For our activation we used ReLU for them. We had a learning rate of 0.00005 and a epoch of 50 and a batch size of 8. Let's see. Our evaluation was pretty good. So for our accuracy, we had an accuracy of 0.87, precision of 0.87, recall of 0.87, and an F1 score of 0.87. And then when we did the k-folds, it went up. So our accuracy was 0.90, and then an F1 score of 0.94. This was a lot better than some of our other models when the k-folds went down. In this case, it actually went up. So then on the right, you have the k-fold huge matrix. Overall, it looks pretty good compared to our one-off results. This is our training and validation curve. It's not too bad. It's a little overfitted, but that's due to our data set being so small. So with the data set so small, it doesn't take that much for the model to learn. And then from that point on, it's just memorizing. So our parameters were learning rate, which was 0.00005, a batch size of 8, our activation is ReLU, and an epoch of 50. Our performance summary, overall for the k-folds, so we had random forest, an accuracy of 0.99, a gradient boosted tree of 0.95, an SVM of 0.97, and a neural network of 0.90. So based off this, our random forest is our most accurate with an almost 100% accuracy. Our lowest one was the neural network with an accuracy of 0.90. So as predicted, proline was a major factor in 3 out of 4 of our models. Flavonoids also had a major impact in 2 of our models, which were the random forest and the gradient boosted tree. It was not in our top feature in our SPM model, but overall it was still our highest one. So some of the challenges and what we learned from this project was that the random forest classifiers work better on tabular data, and a neural network have a harder time with unbalanced data, which was our project, since our data wasn't balanced, with wine 2 having more entries than 1 and 3. And then we also learned the chemical components of wine. And it appears to be possible to identify wine provenance based on chemical composition, which is what we were testing for this project. Some of the challenges were working with unbalanced data. The learning curves were hard to approach in some of our models. And like I said before, the data set's pretty small, so that made most of our models slightly overfitted. Hyperparameter tuning was difficult for some of the models, especially in the neural network. Thank you.
Thank you.